Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to start a very new topic that is called the singular value decomposition for a given matrix A. So, let us do that. So, today we are going to discuss about the singular value decomposition. Now, we have seen that suppose I have a matrix A that is n cross n matrix, then first thing is we have seen that if A is diagonalizable, then I can write A as some P D P inverse. This one I can write, and in this case my D is a diagonal matrix with eigen values lambda, and P is corresponding to the eigen vectors. So, that we have seen that if the matrix A is diagonalizable, then we can write like this one. Now, the second thing is that if A is symmetric, then I can write A as S, S stands for symmetric, just I am writing. Then we can write S as some Q D Q transpose. So, where my this Q is an orthogonal matrix. And in that case we say that this S is orthogonally diagonalized. So, in this case my Q is orthogonal, that is why I change my Q inverse with the Q transpose. So, this form is also called, so I can write this as this form as eigen value decomposition. So, I can write this as eigen value decomposition. So, then we have seen the third form, that when A is not diagonalizable, then we can write A as some, I can write in this form now maybe X, and then Jordan form X inverse. So, this one I can write from here, and this is called the Jordan canonical form. And in this case this X may be, not necessarily I can write, may be orthogonal matrix. So, these things are we have seen. Now, the next thing comes, what happen when A is m cross n. So, in that case what we can say about the eigen values of the matrix A, when so A is a rectangular matrix. So, here we cannot talk about eigen values of A. So, then we start with the new thing is called, so let us write this one as, so I just write the definition. If A is a M cross N matrix, and if lambda 1, lambda 2, lambda n, so I am taking the real matrix, and if lambda 1, lambda 2 to lambda n are the eigenvalues of matrix A transpose A. So, I will take the A transpose A matrix. So, this will be of course n cross n matrix. Then the number, so I take lambda 1 under the root and I call it small sigma 1. Sigma 2 I write lambda 2 and lambda n under the root I will call it sigma n. Then the numbers are called singular values of the matrix A. So, A is a rectangular matrix and we call it the sigma 1, sigma 2, sigma n. So, these are called the singular values of the matrix A. Now, for example, I suppose I take the matrix A. So, let us take matrix A as 1 1 and then 0 1 1 0. So, this is my 3 cross 2 matrix. Then I will take A transpose A. So, this will be 1 0 1 1 1 0 and 1 1 0 1 1 0. So, that is equal to, so if I multiply by this one, if I get 1 and 1 2, this one is just 1, this one is just 1, and from here it is 2. So, it is 2 1 1 2. So, I know that this is always symmetric matrix and its rank will be same as the rank of matrix A. Now, from here I found that the eigen values of A transpose A are, so these are the eigenvalues 3 and 1. So, I got these eigenvalues 3 and 1, and from here I can write that, I can write sigma 1 as root 3 and sigma 2 as 1. So, these are the eigen, these are the singular values of matrix A, that is 1 1 0 1 1 0. So, these are the singular values of the matrix and we write them in the order. We start with the sigma 1, the biggest one, and the, so here this is the order, that sigma 1 is greater than sigma 2, greater than equal to sigma 2. So, these are the singular values of the given matrix. Now, in the first we have seen that a matrix can be diagonalizable, it can be orthogonally diagonalizable, and then we have seen that it can be converted into the Jordan canonical form. Now, after this one we can write that for a given matrix A, that is M cross N. Now, our condition is that we can write the matrix A, decompose this matrix A into, in the form that some u is there, some capital sigma is there, and V transpose. So, the first time we are seeing that A is decomposed into the matrix which contains 3 different notations u, sigma, and V. In all the previous one, this P and P inverse was just the inverse of P. here also Q and Q transpose X and X inverse, but in this case we have U sigma and V transpose. So, we call this that for a given matrix we are able to write this one, then this is called, we decompose this one where U, V are orthogonal matrices, and this is orthogonal matrix means it is a square matrices, and this summation is a diagonal matrices of dimension. So, its dimension will be same as the dimension of A, M cross N. So, I can write not the diagonal matrix, I can write the matrix of dimension M cross N with singular values of A at its main diagonal, So, suppose I have a matrix like this one, and suppose I have this matrix. So, it is 4 cross 2. So, the main diagonal elements will be this one, this, or maybe suppose I have another matrix of this form. Suppose I have a matrix of this form. It is 3 cross 4. So, the main diagonal will be this one. So, this is the main diagonal. So, if we have a sigma is the matrix of order M cross N and having the singular values at this as a main diagonal. So, this is the definition of this one. And now, from here, so if I take this one and we are able to this one, so it is called, so this is called singular value decomposition of matrix A, that is of order M cross N. So, this is I just write as equation number 1. So, let us see that how to find U V transpose. So, the next question is how to find U, V and sigma, all things we need to find. So, let us see that. Now, so we have A is U sigma and V transpose. Let us see what will happen if I take A transpose A. So, A transpose means I am just taking the transpose, and this is U sigma V transpose. And if you see, I can write here sigma transpose. So, this is just I am solving this one. So, I will applying the definition properties of the transpose. So, it will be V transpose transpose sigma transpose U transpose and U sigma V transpose. Now, this is V, and if you see from here, it is orthogonal matrix. So, it will be I. So, from here I can write this sigma V transpose, and I know that this will be of dimension n cross n. So, my V will be n cross n. So, this is m cross n and this will be n cross m, and this will be again n cross m. So, now from here if you see, then this will be equal to V, and this sigma transpose sigma, if you see this one. So, if I multiply by its transpose, I will get only this value. So, this is, I will just write that it will be a diagonal matrix D with this value, where D will be in this case, that will be sigma 1 square up to sigma n square, like this one, because I know that the A transpose A is a symmetric matrix and it is positive definite, and we have taken this, that this is the eigenvalues, and this suppose n cross n, it has n eigenvalues, n singular values. So, that we have written, or if eigenvalues are 0, then it will be 0, no problem. So, this will be here. So, from here I can say that the A transpose A is orthogonally diagonalized. So, and the symmetric matrix will be V. So, from here that this I can write as diagonal form for the matrix A transpose A. So, now from here that I can find my value V by taking the eigenvalues of A transpose A and then finding the eigenvectors. Now, so from here I can write this one. So, maybe I can write this as 2. Also, let us see what is going to happen about A transpose. Now, A transpose is A is U sigma V transpose into U sigma V transpose transpose. So, that will be U sigma V transpose, and this will be V sigma transpose and U, and from here it is identity matrix because it is orthogonal. So, I will get U sigma sigma transpose U, and this is similar, we can write in this form. So, from here I can say that, so its dimension will be m cross m, because A is m cross n, A transpose is n cross m. So, it will be m cross m. So, it is a new matrix, maybe I can write A here D1, and this I can just write D2. So, I can write from here that A transpose is equal to U D2 U transpose. So, it is transpose also here. So, I can say from here that U can be obtained from the solving the matrix A transpose and its eigenvector. So, this is the way we are able to find the value of U and V, and then we can find the sigmas. So, this is the equation number 3. Okay, so, let us see that how we are going to apply the singular value decomposition. So, in SVD basically what we are going to do is, as we have discussed the step 1. So, it means that first we have a matrix A. So, that matrix is m cross n, and this is from R n to R m. Now, I take the matrix A transpose A. So, this is n cross n matrix, and I know that this is a symmetric matrix. So, A transpose A is orthogonally diagonalizable, that I know. Now, we have considered that the rank. So, I consider that the rank of matrix A is K, and I know that this is equal to the rank of matrix A transpose A. So, in this case the matrix, I can write this matrix A transpose A can be written as a matrix V, that is orthogonal matrix, and then D the V transpose. So, D is the diagonal matrix which contain all the eigenvalues. So, I take the eigenvalue lambda 1, lambda 2 up to lambda k, and then it is going to have the 0 eigenvalues because its rank is k. So, I can have the k non-zero eigenvalues and all other eigenvalues will be 0. So, this is my diagonal matrix, and I can take my V as a matrix that is corresponding to the eigenvectors corresponding to lambda 1 V1, lambda 2 V2, lambda 3 V3 up to lambda k Vk, and then corresponding to 0 eigenvalues we will take Vk plus 1, Vk plus 2 up to Vn. So, this is my matrix V, and this matrix will be n cross n. So, that we already know because this matrix A transpose A is n cross n matrix. So, this is what we are going to do in the step 1. So, it is basically step 1. Now, after doing this one, in the step 2 what I am going to do is I will choose the non-zero eigenvalues and I will find out sigma 1. So, first I will choose these eigenvalues and I will put them in the order such that, so I am putting them in the order, and now I am considering that, so I am considering that my lambda 1 is greater than lambda 2 is greater than lambda k. So, this is I am taking the non-zero eigenvalues and I am putting this in the order. So, now from here I am and I know that this A transpose A is positive definite. So, I can take its square root. So, now I am consider sigma 1, I will take lambda 1 square root, sigma 2 lambda 2 square root and so on. Sigma k I can take lambda k square root, and now from here I can say that my singular values sigma 1 is greater than equal to sigma 2 is greater than equal to sigma 3 and sigma k. So, this is the k non-zero eigenvalue singular values of the matrix A. So, this is I will put in the step 2. Now, after doing this one, now I need to find the value of the u, because in our singular value decomposition I am going to do A is equal to u sigma V transpose. So, V we have already able to found. So, now we are going to find u. So, let us take this one. So, this is my non-zero singular values. So, now let us consider the set of image vectors. So, I just consider A V1, A V2 up to A Vk. So, I am taking the k image of the k vectors V1, V2, V3, and V1, V2, V3 is coming from here. So, that we know. Now, so if you see this, then this belongs to the column space of A, and you know that the column space of A will belongs to Rm, because this is a linear transformation from Rn to Rm. Also, since V1, V2 all are orthogonal to each other, that we already know. Now, let us see what is going to happen if I take the dot product of A Vi with A Vj. Let us see the taking the dot product of this, and I am taking this ij 1, 2, 3 up to k. So, I am taking from here the image sets and taking the dot product. Now, let us see, I can write this as a vi transpose a vj, and I am also considering here that I is not equal to j. This can be written as vi transpose a vj, and I know that a transpose a vj, that is the eigenvector of a transpose a, that is equal to lambda j vj. So, from here I can write this as a vi transpose, and this part I can write as lambda j vj, and now from here I can take lambda j common. So, from here I will get vi transpose vj, and this is orthogonal to each other. So, its value I know that this is equal to 0. So, from here this is equal to 0, and from this I can say that a of vi is perpendicular to a of vj, and this is I am taking I and j 1, 2 up to k. So, this is all we are considering about the column space. Now, from here we can say that since all AVI belongs to column space of A, where I is 1, 2, 3 up to k, then from here, and I can say that these are, so the set AVI for I is equal to 1, 2, 3 k is an orthogonal basis for column space of A. So, this is the orthogonal basis for the column space of A, that is we are able to understand from here. Now, so this is the orthogonal basis. So, let us, I say that let us normalize AVI, all this one for this i's. So, for this one what I do, I take AVI and divide by its magnitude, and let us I call this as, because this belongs to my column space of A, so I call it UI, where I is 1, 2, k, and UI is unit vector, because I am dividing this one by. Now, from here let us see that what is going to happen in this case. So, what is the, so this one I am going to do here. So, norm of AVI square I can write as AVI transpose and then AVI. This one I can write as VI transpose A transpose AVI, and this one I can write as VI transpose, and this is my equal to lambda I VI. And now, from here, because A transpose A VI is the eigenvector of this corresponding to eigenvalue lambda I, now I can take this lambda I here, and this is VI transpose VI. Now, VI is the orthonormal vectors, because we have seen that this matrix is orthogonal, because I know that the matrix V is an orthogonal matrix. Is an orthogonal matrix, and each of VI is orthonormal sets. So, from here I can say that this will be equal to lambda I, because V I transpose V I is 1, because this is the orthonormal vectors. Now, from here I can write like this one. So, from here I can say that the norm of A V I is equal to lambda I under the root. So, now from this I can write this as a V I, and this will be equal to lambda I under the root is equal to U I, and that gives me A V I is equal to U I. So, this is the relation we got for 1 to up to k. Now, this thing is from here, and I can write even as this A V I is equal to sigma I U I, if you want to write in the term of singular values. So, I can write this one as, because I know that this are the singular values. Of A. It is a non-zero singular value, because all zeros are also there. So, we are writing the non-zero singular values, we are concentrating on that one. So, I get this value A V I is equal to sigma I U I. Now, from here I can say that, so the set U1 U2 UK is an orthonormal basis for column space of A. Now, what we want? We can extend this set to an orthonormal basis of Rm, because this belongs to Rm, and these things we can do with the help of the Gram-Smith process, or we can, because in this case we also know here, we know that the column space of A is perpendicular and orthogonal to the null space of A transpose, that we know, because if you see we have the picture of 4 subspaces. So, in the Rm we have, this is the column space of A and this is the null space of A transpose, and they are perpendicular to each other. So, now I know that the basis of this column space are also orthonormal set, it is the basis of this one, and I want to extend this one. It means I need all the vectors which are orthonormal to all these vectors U1, U2, UK. So, I can choose the vector from null space of A transpose, and that is also orthonormal, and then we are done. So, we can extend this set of orthonormal bases of Rm to make my a orthonormal basis of Rm. So, we can extend U1, U2, UK, and then I can have UK plus 1 and UM. So, this one we can extend very easily. So, after getting this value, so this is my basically, and so let's instead of U I just write something, maybe I can write as basis B. So, after doing this I make the my matrix U. So, U matrix I will write U1 first column, U2 UK, uk plus 1 and um. So, this is a column I am writing, and this matrix will be of m cross m, because all this ui belongs to Rm and m in number. So, this is, so now from here I can write that I want to see what is my u sigma. Now, u is this one, u1, u2, um, sigma, it will be corresponding to the largest singular value lambda 1, then lambda sigma 1, sigma 2 up to sigma k, and then I can put the remaining 0 eigenvalues here. And I know that this is of order m cross m and this is of order m cross n. Now, if I multiply this one, I will get u sigma 1 u1, sigma 2 u2 and sigma k uk, and then I will get 0 uk plus 1 up to 0 um. This I will get, and this is what, this is equal to sigma 1 u1 is a v1. So, that we have seen from the this one, yeah, from here. So, a v I is equal to sigma I ui. So, I am getting sigma 1 u1. So, sigma 1 u1 is a v1. So, similarly, I can write a v2, a vk, and 0. So, if I put it here 0, so then it is, this value is coming 0 0 0, and if you see from here I can write this as, so this zeros I can write as, so now from here I can write this as a v1, a v2, a vk. I can write this as a vk plus 1, because that is going to have a 0 eigenvalues, a v m. So, it everything depends upon that, in this case which is greater, whether m is greater or n is greater. So, it will go up to, because we know that our matrix V is of n cross n. So, now from here I can write my u sigma, I can write as my matrix A and taking V. So, V is the number of 0 0 up to this. So, these are the vectors that is coming from the as a 0 eigenvalues. So, I will get this matrix here, and I can write this as my n cross n matrix with A. From here I can get these values, because this will be of order m cross n. So, m is the number of rows and n is the number of this one. So, I will get up to n here. So, this will up to n. If you do this multiplication, so if you see from here it is going up to n. I think I should take this is equal to n. So, I can go up to 0. So, maybe I can just write here, I think instead of this writing I should write like here. So, I should write it like 0 0 0. So, and this is of the dimension m cross n. So, that we are writing, because from here I get the matrix basically of or m cross n, and this value put as a u1, a u2. So, this is also this of order m cross n, and then I will get this value. This one I will just write in this form. So, after doing this one I will get this matrix A, and this is V n cross n matrix. So, from here I can write that after doing this one I can write my matrix A, that is u sigma V transpose, and that is my SVD. So, this way we are able to find all the elements of the matrix V and all the elements of the matrix U. So, now after doing this one, we can take a quick example, then how we can find the SVD of a given matrix. So, let us take the example, find the SVD of a matrix A. So, this matrix we are taking 1 1 0 1 1 0, and this is 3 cross 2 matrix. So, in this case, if you see now, my A transpose A will be 2 cross 2, and my A transpose is going to have 3 cross 3, because A transpose is 2 cross 3. So, it will be 2 cross 2s, and A transpose is 3 cross 3. Now, we will go with the first step. So, let us take the solution. So, first I will find out A transpose A, and this is my 1 0 1 1 1 0, this is 1 0 1 1 0, and if you see from here, then this is I am getting the value 2 and 1 1 2, and if I find out the eigenvalues of this one, so A transpose A minus lambda I, so that gives me the lambda minus 3 into lambda minus 1, and that is equal to 0. So, this gives me eigenvalues 3 and 1. So, these are the eigenvalues I am getting. Now, corresponding to the eigenvalues, I want to find the eigenvectors. So, I have my vector. So, corresponding to lambda is equal to 3, my A transpose A, if you see, then I can write from here, I want to write it is V1 is equal to 3 V1, that gives me. So, I have my equation 2 1 1 2, and I want a vector that should be equal to 3 times of this vector. So, I can choose this vector as a 1 1, because it is 3 3, and from here now I want to make this vectors orthonormal also. So, this is a vector and I want to normalize this vector. So, I just take the V1 vector as 1 by root 2 and 1 by root 2. So, I have normalized this vector and I have taken the first eigenvector as this one. So, after doing this one, now for corresponding to lambda is equal to 1, I will go by the same way. So, I have 2 1 1 2. So, I want this one is equal to 1 time this. So, if you see from here, I can write 1 minus 1. So, it is 1 minus 1 1. So, I can write 1 minus 1. So, that is there. So, now I will divide by this one. So, I can choose my V2 is again 1 by root 2 and minus 1 by root 2. Now, based on this one, I can show that my A transpose A can be written as, so now my V is the matrix which is corresponding to 1 by root 2 and 1 by root 2 and 1 by root 2 minus 1 by root 2. So, this is my matrix and this is an orthogonal matrix. So, I can write that this is equal to V D V transpose. So, this is we are able to get. Now, I will find out the value of ui's. So, now from here my sigma 1 is root 3 and sigma 2 is 1. And if you see that my A is 3 cross 2, so my u should be 3 cross 3 sigma should be 3 cross 2 and V transpose is 2 cross 3. Sorry, 2 cross 2. 2 cross 2. So, this one we want. So, we got this value. Now, my sigma, if you see, my sigma will be, so I will put my sigma 1, the largest one here, then sigma 2, and I will put 0, 0 here. So, I will get 3 cross 2, so I will get 0 and 0. So, this is my sigma basically. Now, from here I need to find u. So, if you see from this A transpose. So, A transpose, if you write, so it is 1 1 0 1 1 0 and this is 1 0 1 1 1 0, and if you say this one, so it will be 2, then it will be 1, it will be 1, then it will be 2, sorry, it will be 1, because I am doing this one. Now, doing this, it is 1, and doing this, it will be 0 and it will be 1, because this one I am taking 1 and this one I am doing this, so it should be 0 and this is 1. So, it is a symmetric matrix, so I know that, and this is 3 cross 3. Now, if you find out its eigenvalues, so you will find out the eigenvalues of A transpose. So, this is going to have the eigenvalue 3, 1 and 0, because if you see, then it is a 3 cross 3 and the rank of A transpose is 2. So, it is going to have 1 0 eigenvalue. So, it is a singular matrix and going to have 0 eigenvalue. So, this is what we got from here. Now, I want to find the value of u1 u2. So, either you can solve this one and find out the eigenvectors, or we have the way we discuss. So, what we need to do is now, so I want to find the eigenvectors. So, I will start from here and then I will try to find what is my, so I know that A V1 is equal to sigma 1 u1. So, from here my u1 I can find that A V1 divided by sigma 1. So, sigma 1 is root 3 and this is my A, and I can put my V1. So, V1 is 1 by root 2 and 1 by root 2. So, it is 1 by root 3 here, and now if I, so it is 2 by root 2 and this is, I will get 1 by root 2 and 1 by root 2, and from here I can write this vector as 2 by root 6, 1 by root 6 and 1 by root 6. So, this is my u1 and it is a vector with magnitude 1 that we can see from here. So, I am able to get this value. Now, corresponding to, I will get my u2 as A V2 by sigma 2, and that is sigma 2 is 1 here. So, I will get this value, and if you solve this one, I will get my value 0 minus 1 by root 2 and 1 by root 2, because I just substitute the value here for V2 and I get this value. So, now we are able to find the 2 from here. So, and you can see that this u1 and u2, that is belongs to the column space of A, and they makes the column space of A. So, these are the column space of matrix A. Now, I want to extend this one. So, that is my question, because my U is 3 cross 3. So, I am able to find these two eigenvectors, or maybe these vectors u1 and u2 based on this condition that AV1 is equal to sigma 1 u1 and AV2 is equal to sigma 2 u2. Now, I can take my u3 that should be perpendicular, should be perpendicular to the column space of A. Only then it will be going to make the orthogonal basis for R3, because our matrix is moving from, it is 3 cross 2. So, it is from going from R2 to R3. So, now, so perpendicular to column space. Now, what we do that we just, for the calculation, we can make life simpler. I can take my u1, so under root 6 I can take on from here. So, I can write from here that under root 6 u1 is equal to 211, or I can similarly I can have under root 2 u2 is equal to 0 minus 1 1. So, just to make this life simpler, and this belongs to column space of A and also belongs to column space of A. So, now what I do, let my u3 is a vector x, y, z, because it belongs to R3. Now, it should be perpendicular to both, because these are the making the basis for the column space of A that we have seen. So, it means that the dot product, so I just put this as a row vectors 2 1 1 and 0 minus 1 1 and taking x, y, z dot product. So, it should be 0 0, and from here you can see that this is going to have a basis 2. So, now its rank is basically 2. So, now from here you can see that I can have my 2x plus y plus z is equal to 0 and minus y plus z equal to 0. So, I can have y is equal to z. So, from these two I can have the vector. So, y and z should be same in this case, and 2x is equal to this one. So, maybe I can just take this vector as, I just take is as A, or maybe I can take minus A, because this will be the minus sign. So, I just take minus A, some minus A, and from here minus A minus 2A, it will go 2. So, it will be A, and from here I can take this vector as 1 minus 1 minus 1. So, and now I can normalize this one. So, I can choose my u3 as just dividing by its magnitude. So, I can write a 1 by root 3 minus 1 by root 3 minus 1 by root 3. So, 1 by root 3 minus 1 by root 3 minus 1 by root 3, this one I can take, or I can choose my A is equal to minus 1. So, I can also choose my u3 as minus 1 by root 3, 1 by root 3, 1 by root 3. So, I can choose any one, you can this both the u3 if you see. So, I can say this or this is equal to this if A is 1, and this is equal to this if A is minus 1. Everything depends on this one. So, but this and these are orthogonal to each other, that should be there, and if you see that taking the dot product, so this will be orthogonal to each other. So, this way we are able to find the value of u, and now I can write my matrix U. So, it is equal to my V1 is 2 root 6 1 root 6, 1 root 6, my u2 is 0 minus 1 by root 2, 1 by root 2. So, this is I am able to find, and then maybe I can choose any one. So, I just take minus 1 by root 3, 1 by root 3, 1 by root 3. So, I have taken this value. So, maybe you can that this value we have taken corresponding to just we want to have a less number of negative sign. So, that is why we have taken this one. So, my this is u, that is 3 cross 3, and from here we can verify that my A matrix should be equal to V transpose. This we maybe verify in the next lecture. So, I will stop here. So, in the today's lecture we have discussed a very important theorem that is called the singular value decomposition of a given matrix, and then we have seen that how we can generate the value of u and v, that is the matrix involved in the singular value decomposition for the corresponding to the given matrix A. So, in the next lecture we will show that how we can compute this singular value decomposition taking the help of MATLAB or Octave. So, I hope that you have enjoyed this lecture. So, thanks for watching.